Uh, Dr. Darbar, can we start?
Yes, please.
Okay, so I'll get it going. Okay, so good evening and welcome to the eighth edition of Engineers Day commemorative asset colloquium today. For those of you who are from outside the TIFR family, uh, a couple of words about ASSET. ASSET stands for Advances in Science, Engineering and Technology. The ASSET is one of the three weekly colloquia which are organized in TIFR, the other two being of the natural sciences and mathematics, which are held on Wednesday and Thursday, respectively. And of course, ASSET colloquium is held on Fridays at 4 p.m., the way it's happening today. ASSET organizes colloquia mainly in the areas of engineering, technology, popular science, medicine, and so on. In fact, it has hosted many eminent personalities like the one you're going to talk to today, listen to today, from both from within and outside India, including many Nobel laureates and field medalists and so on. Engineers Day is celebrated on September 15th, was today, which is the birthday of Bharat Ratna Mokshagundam Visvesvaraya, the most loved and well-known engineer the country has ever produced. It's often said that he utilized every minute of his long life. In fact, he lived more than 100 years for excellence of the nation. His contributions, in fact, many of us know only as an engineer, but his contributions to engineering, industry, agriculture, and even commerce and banking are too numerous even to list here. So it's always a great pleasure for the ASSET to organize these series of commemorative colloquia. In fact, this, as I said, is the eighth edition of Engineers Day ASSET colloquia. So to just in a minute to kind of say who are our past speakers. In the year last year, 2022, the talk was given by one of our own, Professor R.G. Pillai from TIFR. The year previous, in 2021, it was given by Lieutenant General Harpal Singh, who is the Engineer-in-Chief of Ministry of Defense headquarters. In 2020, the talk was given by Professor Subhashrish Chaudhary, Director of IIT Bombay. The year before, it was given by Dr. Gautaman, former Distinguished Scientist and Chairman, PRC Safety Council. In 2018, it was given by a team Indus, a set of three very young engineers who are actually building at that time, the moon landing, and also the rover system as a potential candidate. Now, after 5 years, it was a reality that actually we had Chandrayaan-3, which actually landed in moon, and they were very exciting times we are going through right now. The year before, in 2017, it was again given by one of our own, Professor Vijay Raghavan, that time Secretary DBT Government of India. And the series actually started with talk by Dr. Satish Reddy, who was scientific advisor to Raksha Mantri at that time in 2016. And as you all know, today we are going to have Dr. Hemant Darbari, Mission Director, National Supercomputing Mission, going to talk about India's march towards exascale supercomputing. ASSET would sincerely like to thank Professor Jairam Chenglur, Director TIFR, for making this colloquium possible. On behalf of the Institute and ASSET, we would like to sincerely thank Dr. Darbari for accepting our invitation for his talk, for delivering this very special colloquium. In fact, he is a bit unwell. That is how you couldn't make it in person at TIFR, but in spite of that, he really wanted to ensure that the talk goes uninterrupted and as scheduled. So we sincerely thank him for that. Just a couple of minutes on formally introducing Dr. Hemant Darbari. As I said, he's the Mission Director of National Supercomputing Mission in India. He's an alumnus of IIT Roorkee and University of Allahabad. He's a founding member of the Center for Development of Advanced Computing, that is what we all know as CDAC, And before taking over the current assignment, he was actually the Director General of CDAC. He has a vast experience of more than 3 decades in the areas of artificial intelligence, machine translation, and high performance computing. As a Director General CDAC, he was responsible for building capacity and capability for R&D in the multi-specialty domains of HPC, multilingual computing, software technologies, health informatics, disaster management, e-governance, and education and training. He has also designed, developed, and executed very large projects of national importance. Of course, he won many awards. Just to give a few of them, he is recipient of prestigious Computer World Smithsonian Award medal for his work on Mantra, which stands for a machine-assisted translation tool, I'm sorry, and the Vasvik Award for his contributions to the advancement of information communication technologies. He has also received the Award of Excellence in Corporate Leadership at IIPS in 2015, and the Vishwa Hindi Samman for his contribution in the field of Hindi language computing research and development. I think with these few lines of introduction, it's again great pleasure for me to formally invite Dr. Hemant Darbari for this call. Over to you, sir.
Thank you. So I'll just share the screen.
Sure. Perfect.
So, Dr. Jairam Chengaleru, Director TIFR, Dr. Satyanarayana, Coordinator Asset Forum, Member of Asset TIFR, Dr. B.S. Jagdish, eminent alumni of TIFR joining from all over the world. I consider this a privilege and a great honor to be presenting before such an august audience. It's a big day today as we are celebrating the Engineers Day to commemorate the birth anniversary of Shri Mukagum Visheshwaraya. He was a pioneer in the flood disaster management and control. He presented and installed the irrigation system with water floodgate at Khadakwasla, Pune. He was bestowed with the Indian highest honor of Bharat Ratna in 1955. In today's world, the flood and cyclones are the most disastrous event, and all-out efforts have been made to predict these events with the extensive use of supercomputers and to have human life and properties safe. This is one of the many use cases of supercomputers. And today, I will be talking about India's marching towards exascale supercomputing. Are the slides visible?
Yes, but it's not moving. Are you still on the first slide?
Yes.
Oh, okay, fine. Now it is second slide. Yeah.
So currently, we are working on a national supercomputing mission. And this is the mission which has been crafted by CDAC and ISC and funded by Ministry of Electronics and IT and Department of Science and Technology. The program started in 2015, and the supercomputing infrastructure across the country, we have provided 30 to 40 petaflop of power. Supercomputing ecosystem and capability has to be built, and we have indigenously developed the supercomputer, be it HPC processor, the server board, the high-speed interconnect, the Trinetra system software, and system software stack. The the systems which we have been developing are all indigenously done in India. And what we are trying to build is the totally indigenous supercomputer, which will be Exascale. So this is our first step towards taking up the Exascale to the masses. There are supercomputing applications also we tried out, be it bioinformatics using cancer research, drug discovery, and many applications in the bioinformatic domain, the flood forecasting and disaster management, urban environment and weather modeling, seismic data processing for oil and gas field, material science and chemistry, and AI applications and languages. We have also planned to have a capacity building or training HPC aware manpower around 20,000. So we have already done around 15 systems deployed all over the country in phased manner. And the supercomputing infrastructure currently usage till date is around 2,600 HPC users from 19 institutions across the country. And around 60 lakh HPC jobs were executed. Compute power worth 60 plus crores used by the scientists and researchers. And the original target of 30 petaflop was there, but now we are going to build something around 62 petaflop systems in the current budget. Now, from the R&D perspective, we have already done a system building. The architecture, design, and integration of the building blocks have been done. The supercomputing systems, system software ecosystem has also been created by us. And the team is very efficiently working on the integration of HPC, AI, and big data, which is now getting converged. So I'll talk about these things in my later slides, but this is what exactly is the major contribution which we have done from the R&D in the build part. The Rudra server, which we have created, is first in the country. And this server is all indigenously designed and manufactured in India. And now we have already built the system, and this is at par to any of the system in the world. IISc also has initiated academic research projects in this system side as well as in the applications. So we have already trained something around 17,000 plus HPC resources, and we are trying to see how these things can be multiplied. So from the system side, if you see the Rudra server board was a unique work which we have done, which is a open 19 factor form factor board, which gets into the rack. And then finally, we could create a system out of it, which is a 4-node cluster. And this is where we tested all our softwares, all the system softwares. And now this will be the building block for taking up a 20 petaflop system, which we are going to deploy soon. So it's a totally Atmanirbhar Bharat system. We have also done a full POC of that, and now it is under manufacturing. And the VVDN, which is in Manesar, is actually going to manufacture something around 6,000 boards, and will create systems around that. So if you see that the processor speed which we have picked up in Rudra is 2.6 gigahertz, as well as the other systems which are using 2.9 gigahertz chip, we are still performing much better than what exactly is happening in the world. Like NAMD, WRF, OpenFOAM, PROMAC, all these applications are very, very effectively been used, and the benchmark results shows that we are at par or better than what exactly we have been building. So we have over 85 lakh jobs now to date. We have run on our systems across India. Param Shivaya was the first supercomputer which was built and deployed at IIT BHU and it was inaugurated by Honorable Prime Minister in 2019. Brahma is in IISER Pune and Shakti is in Kharagpur. There are now 15 such systems which have been deployed all over India. So this is the landscape you can see, and this is what exactly we have been deploying systems. And from 2019, which is the first supercomputer which we gave it under the NSM. And now we have multiple systems which have been deployed. So a lot of hard work and hardware we created, and now that is now being put up into the systems. And now these systems are going to be exploited and been used by the researchers, not only India, but even abroad. Yet another milestone was Param Siddhi AI. This system was built at CDAC Pune, and this is a system which is used for the AI workload. And this system has a full capability of 210 AI petaflop. And recently, in June, we added Arawat to this system. And now we have 410 AI petaflop system, which is the fastest supercomputer in India. And it ranked 75th in the top 500 list of supercomputing. So now this whole system is available for the researchers, the startups, the industry, and the total academia to use this system and can get benefited out of this whole compute which is made available. As far as Siddhi and Rawat integration is concerned, we have been very successfully done that. And now we are trying to see how we can create a one AI exaflop system. And we can provide this as a AI compute cloud to the researchers. So if you go by the phase-wise stuff, the 3 systems which were assembled, 12 systems in the phase 3 were manufactured in India, and now 15 Param supercomputing facility are designed and built in, and where we are going to get 24 petaflop of compute power. And the phase 3 system, which is a designed and manufactured system, we will be adding up something around 40 petaflop, and 9 systems, including Param, National Param supercomputing facility, will be created. And then the total compute power will become 64 petaflop with 24 HPC facilities across India. Academic usage, if you see, then we have already installed in academic researcher institutions is 38 petaflop with 21 HPC systems, and 3 systems we are targeting for the commercial use, which is Param Utkarsh, Param Siddhi AI, and Param Siddhi for the national facility at CDAC. These systems are all been deployed at CDAC, and that will be given as a commercial for the commercial use to the industries and startups. The supercomputing infrastructure is currently very extensively used, like 4,900 HPC users from 100 institutes across the country are using that, and huge amount of PhDs and publications have come up using our compute. 5 major applications were targeted, and one is the NSM platform for genomic and drug discovery, then urban modeling, then flood forecasting, HPC software suite for seismic data processing, and MPP lab. And we are also hand-holding people to do the application porting, optimization, and scaling of their code. This is again a major work which has been done under NSM. So if you see, the key deliverables become from the infrastructure side, the Rudra, the Trinetra, and we are also designing our own chip, which is OM processor. And with that in hand, it will be, the system will be at least 85 to 90% indigenous. So OM series of processors also are under pipeline, and those things will be done, wherein we will do the CPU as well as the GPU development. The various system software stack part has been done, then OM processor will be a 96 core initially, and then we'll see how the things will move on. So various applications, as you see here, drug repurposing and cancer research and drug discovery has been done. And this was all during the COVID period. We very extensively used these systems and took 3,500 molecules, and we tried to do the drug repurposing. And we could identify this remdesivir and ivermectin as the drugs which will be very useful for the COVID. And we all know that that was the drug which is very effectively used. Similarly, Giloy and Pimpli from the Ayurvedic side we simulated, and that also became a reality that that was used. So what I'd like to say is that from the compute simulation side, if you see, we have very extensively worked on these systems and gave meaningful results for the masses. So this is one major success story which we already have. Similarly, this is a simulation of various weather predictions, the disaster management, and oil reservoir modeling. These simulations are all done onto the current systems, and we are very happy to say that the target which was set to us from the infrastructure side, from the R&D side and HRD side are all being met. And apart from this, this target which was given to us, we also created beyond the approvals, and we have very successfully delivered these things. And we have one more year to go, and most of these things we'll try to deliver within this period of time. So now moving to the next level, this exascale supercomputing through harmony of innovation, because exascale cannot be done in a run-of-the-mill type of methods. So a lot of disruptive technologies are to be created, and those disruptive technologies can be created in synergizing with the researchers, coming up the system software guys, the application people, the hardware people. They have all to come together, craft out solutions, and deliver. So that is what exactly is the key. We definitely will have to work out a plan how we can take it up to the next level. And if you see, currently the systems have moved from terascale to petascale and now to exascale. And from the exascale side, we have actually done excellent work as a preparatory things during this period also. So I'll talk about that. So from the gigascale to terascale and petascale, and now we are moving to exascale computing, which is 10⁻18. And we call that as Param Shank. So our vision is to establish dependable and secure exascale ecosystem with innovative design, disruptive technologies, and expert human resources. Our mission is to develop hardware encompassing of exascale chip design and manufacturing of the exascale server board, exascale interconnect, and storage including silicon photonics to exploit huge amount of opportunity which we have in the system software and high-end software development to make India a global leader and develop solutions for grand challenge problems for the national and international level. So if the question is asked, why Exascale? It is to build Exascale capability system is key enabler for accelerating scientific discovery in the world. And there is a strong correlation between research output and acceptability of HPC systems. Scaling from tera to peta to exa, leading to zeta scale computing is the key to futuristic research problems and providing state-of-the-art solutions to grand challenge problems. Each of these solutions will have a widespread social impact. So this is what exactly I told, that we should all make in India and Atmanirbhar Bharat. We'll all develop our own servers, high-speed interconnect, storage, as well as the microprocessor. And Paramshank will be realized in the form of Atmanirbhar Bharat mission. So this is the Paramshank, which we have coined that word because in Indian numbering system, 10 raised per 18 is Shank. So we have given the name as Paramshank, and we are trying to realize that. And there's a huge amount of research and a big jigsaw is to be solved. So we have to come together to pick up a piece of jigsaw and work in consortia to deliver systems and make the real Exascale indigenous machine. So various components have been picked up and those things can be done. Now, if you see the grand challenge problems demand Exascale computing are the numerical weather prediction is definitely one of the most important factors, and that is what exactly was our Sir Visheshwaraya has worked long time back in 50s and got the patent on that, the work which he has done for the flood monitoring. So similar type of work we are trying to do here in the monsoon mission, in the climate modeling. The material research, again, there's a new design of a new material is possible. Then oceanographic simulation, which there's a deep ocean mission, which has been initiated by the government of India. There again, huge amount of compute will be available because a lot of data is going to be collected from the underwater, and that is to be processed in real time and take up to the next level. And faster real-time simulation is again very important because this electrical grid failure, which has happened in the past, even the rail accidents, can be avoided by doing a faster than real-time simulations. And those simulations will always be requiring huge amount of compute. Then the grand challenge problem of like crypto analysis, digital twin is yet another area which is very, very important. And we are trying to see how we can do a digital twin for smart cities and chemical process plant for digital twin. And then creating energy efficient enzymes, then computational fluid dynamics, the CFD, then bioinformatics is a ab initio molecular dynamics and personalized medicines. And if we can see how we can come up with the new periodic table with the cluster of atoms. The list is very long and many, many things are to be done. And with the work which we are doing in some form, we have already come up together, and what we can do together, I'm going to present it now. And this will lead India towards technological supremacy in the global arena. So if you see from the supercomputing target side, we have indigenous development technologies, as I talked about. Then we want to do a talent creation and applications also. Then we can have a global partnership and we can work on various engagement models to work in the domains of basic science, earth science, digital twin, engineering applications, defense and atomic energy applications, and major work which we are trying to see how those things can be brought into the mainstream. Then future is definitely the exascale system, and all these systems will be required to be built from scratch in India. So these are the major work which we are trying to do into the NSM, and NSM 2.0 we are crafting, and in that we are trying to address all these domains and all this work. And I'm really happy to state that with the interaction with the even with TIFR, with the IUCA, with the VSSC, and a lot of places, all the engineering applications which have been done, we are very, very closely working with these researchers to see what exactly can be done and how those things can be brought into the mainstream. And we can solve the problem of same jigsaw which I was talking of, and which is a complex jigsaw for the exascale supercomputers. So various areas in which the work is going to be undertaken is that the scientific data processing, seismic data processing, the earthquake prediction. Earthquake prediction is a major research area on which the worldwide people are working. The Oak Ridge National Lab and all these consortia has been there. They are working very extensively to see how those things can be brought in, because that's yet a problem which has not yet been solved in the healthcare, in the digital twin side, in the AI applications. So a lot of work has been done into this area, and we are trying to see how we can come together and make the things together. So if you see here, this plot shows that we are going to provide something around 10 petaflop to 100 petaflop to 200 petaflop and 500 petaflop, and move towards the exascale system. And in the upper side, what we are trying to say is what science can be done and what level of things can be done through on these systems. And below we say that what will be the impact of that. So this is how we have captured the whole thing. So major work which has been done into this area, and the researchers, we are trying to come together. So we are going to float RFP from this mission, and we'll invite people to work on these specific topics in a consortia mode and deliver in time. So that is what exactly is India is marching towards. And we are all trying to see how we can come together, synergize together, and the expertise, whichever expertise is available with any institution or any individual, if they can come together and start delivering, that will be very, very good thing to happen. So this is what exactly we are trying to do. So this is for the life sciences. If you see, these are the application genomic-wide association studies, then even population genomics. And so these type of things can be very effectively done, and can be done only if we have a high throughput, high compute systems available. So that's where we are trying to see how we can bring these systems to the people and the researchers and the startups and industry, and give them this the system, and the various teams can provide their research outputs on a much faster pace, because the things which are not possible earlier are definitely going to be possible now. So this is a typical application of exascale, when you can have a COVID-19 virus, then the heart protein, then cancer protein. Cancer work also, we are doing a lot of work onto simulation of P53 cancer protein, and CDAC, even TIFR and other places. The huge amount of work required to be done, and a lot of data is now available, and data analytics and those type of things required to be done on bigger systems to get the things much faster. So moving to the astronomy and astrophysics, this is the work which has been presented by the IUCA here, Inter-University Center for Astronomy and Astrophysics, where they are trying to see how the simulation of astrophysical flows, then expanding horizon for various areas, and even the big data from the mega projects that can be brought in. So that is the science part, and what will be the impact of that. That is also been presented in the same form, that if these type of compute are made available, how that thing can be very effectively brought into the mainstream. So like this is the simulation of astroflow, that sun and planet, then the black hole science, all these things can be very effectively built, and the large scale structures can be worked out. And all this work has been very effectively done at the IUCAD team and the consortia, international consortia also. So like LIGO you might have heard about the LIGO work which has been done, and now LIGO India is also got approved, and we are going to provide the compute need of the LIGO through our this exascale computing part. Similarly, SKA will be a very important thing to be worked on. This is the GMRT work which the IFR has done, and I'm very happy that we have definitely, we are working on this system, and this system we definitely would like to see how we can provide that technical support, and this system going to be deployed at the site, and we are going to provide a 1 petaflop system, wherein, because the data movement is a big problem, so if we can work it out, that is what exactly has been done. And this is 2000 beams the real time can be shown, which is going to be the largest for next 20-30 years, because Meerkat will be which is having only 400 beams. It will be much 5 times faster than that. So this work, I think, is the work of Jairamji only, and he knows better, but I thought it's worth mentioning that this is again a very important field which we are embarking on. Now from the nuclear physics side, this is again from the TIFR. This work we are trying to bring it to the mainstream and try to see how we can work together and take the things to the next level. Yet another area which we are trying to work on is the modeling of the origin of the universe in less than 1 second. And this is again very, very important work, how this Big Bang happened and what exactly can be seen on. And they again require a huge amount of compute. Similarly, chemical sciences, this again from TFR side, we are trying to work together and try to see how those things can be worked out. Then quantum matters, we can work out together and see how this around 20 petaflop large memory will be enabled to produce precise results on materials and energy applications. Then this type of work we can do. From the earth science side, there's a depression cyclone, then probabilistic forecasting. All these things can be done on these large systems because of the fact that the compute model is very, very important to be created and can run on a real life system. And these systems can provide the simulations, the big data analytics, and the basic fundamental science can be done. So now this work of this model, which has been indigenously developed by IITM, this is Ministry of Earth Science, that has been taken up, and we can go to 2 square meter type of thing. This huge amount of compute is required. Similarly, if you see this river basin simulation, if you take a current 10 petaflop system, which will take 178 hours, can get reduced to just 2 hours. So this type of speed ups we definitely need for anything which you want to do on a large scale and a real time. So that has been planned. So the impact is that the mesh size, as we increase, the level of detailing which we can get, and the decision making becomes that much good. In the flood indentation prediction side, when a 900-meter square mesh has been taken up, the indentation map shows the second picture. But if you see the 100-meter resolution, this gives a much neater and much better prediction of what areas are going to be inundated and how the things can be managed. This is what exactly is going to lead towards the major exascale computing, and which is a digital earth, which we are going to also be becoming a part of this consortia, and that we'll like to bring in. I was just talking about the earthquake model, and this is again a very, very important thing, because earthquakes till date are not predictable. And if we can do a early warning, planning and warning model for the earthquake, that becomes a very important area on which we can all work together and try to see how we can provide solutions. Similarly, in the digital twin side, if we see that we can do a simulation, because currently, like when you do a flood prediction, so what do you require? You require three things. One is that how much of water will be coming from the river side or from the seaside. Then there is a urban modeling, that how is the drainage system and how the things are working. And based on that, you can actually go for how much of water level will be there at each particular road. So more meaningful stuff, more meaningful solutions can be provided if we can give a prediction of that sort. And then it will directly impact the masses and the actual citizen. So this is what exactly has been planned. Then similarly, traffic is another example. Huge amount of compute is required to really handle this type of data, and then finally come up with what solutions can be created. So all these things can be part of the thing. Even the safe city components, they all require huge amount of computing, and they can be very effectively taken up to the next level. So another thing which we are doing with the NCL here, which is a DME plant, digital twin for DME process plant. And this is, again, is a patented work done by the NCL. And this is a replacement of the diesel and petrol. And for this, a plant which has been created by them, that can we have a digital twin of that. So what happens is that when you are going to design a new plant, you can do it all on a digital twin and then take it up to the next level. Whatever error is going to happen, this is again one of the example of a faster than real-time simulation, because you can always predict what is going to happen, and then based on that prediction, so a lot of things can be done, and those interlocks can be set, and then those things can be very effectively taken up by the system by itself. So some of these type of things are also been planned. Similarly, this speech-to-speech translation systems are going to become a reality now. You have all heard about the ChatGPT and the work which is happening. So Vachantar speech translation system, speech-to-speech translation system can be one of the major work which can also be utilizing these huge amount of compute, because we have 22 official Indian languages, and we can converse in our own Indian languages and I can talk in Hindi, you can listen in Marathi or something of that sort. So this again is a very important activity which is we are trying to bring into the table. Similarly, there are different architectures from the hardware perspective. where we can very effectively build these systems and these applications. If they require different class of architecture, they can use that. So this is what exactly our concept is, that in the exascale supercomputing side, what we will do, we will create different type of architectures. We will try to create these architectures at one place, and these systems can be very effectively used by the researchers. So if a class of architecture is going to be useful for an application, that application can use that class of architecture. And this is what exactly we are calling exascale supercomputing complex. And this complex will have 4 to 5 different architectures. There are places where you can definitely have a high bandwidth requirement. There will be something require the large memory models to be run on. So all these things can be brought into the system, and those systems can be then integrated into one such place where you can get an access to all. And then the scheduling can be done based on what exactly is required to be accessed. Now, there's a fact that these systems are going to be very, very power requirement of these systems are very large. So these systems cannot be placed at many places, even within the country. So we definitely will have to have a system which is going to be deployed, and that is what we are planning to be deployed at Pune. And now the point comes in, when you have a system stationed at Pune only, then how the data is going to come to this large system, because huge amount of data is to be transferred. So from that perspective, also we are trying to make a secure distributed data grid. And this data grid will take the data from A place to B place on a high-speed fiber optic network with at least 400 gig type of transfers. And with this data movement, I think as soon as the data reaches the supercomputer, this can be executed on that. So this is again a pilot. We are doing it, and we are successful on that. Then that will be again a major game changer, because the data resides at various places, and how to take it to the real big supercomputers is a big challenge. So we can definitely try to capture that and try to see how we can take it up to the next level. See, yet another work which is we are doing is a compute cluster node software stack, and all these layers are all being done from scratch. And this system can be deployed on the existing system, and they can all be networked. And then this whole system can be effectively brought into the users. So, and we have to see how this integrated development environment can be worked on. And we try to see that how this HPC big data and AI programming environment can be created, because there's a speed, reliability, scalability of the software components have to be very effectively seen. The workflow libraries and from the petascale to exascale systems have to be very effectively built. So this is another area which we are going to work together, and where we can very effectively work on various algorithms, various data programming environment, how we can make it easy for the users to exploit the bigger systems. So this is how the whole thing can be brought in. And we can very effectively see that this becomes a very crucial part. And later on, what I could see is that the quantum also can be integrated in the same software environment. So yet another major work which is required to be done is onto the processor side. And this is the roadmap which we are trying to work on, and from RISC-V based processors to ARM based processors. And then finally, we will integrate your HPC AI converged processor. That's how we are planning, and this is what exactly will be the our roadmap for taking the HPC processor, HPC server, storage, the interconnect, system software, and even the application software, all done indigenously. And that is what is going to be the future. So if you see that the hardware processor controllers, the software, the algorithm, the application, the quantum simulator, quantum accelerator, the silicon photonics, yet another area which is very, very important now for the speed transfer, high speed transfers. And this is how the whole thing can be made available on a cloud, and that will be the Param chunk. So this is how the whole thing is being orchestrated, and we can very effectively see that all these things put together will take India to the next level and maybe on a very fast track. So this is what I would like to say here, that if you just run through it, we started way back in 1988, 89, wherein Cray was refused to India. At that time, we decided that we will not only design, develop, but also deploy the indigenously developed supercomputer. And I, being the founder member of CDAC, I was part of this whole journey. And I'm really happy to tell you that it was very, very happy moment for all of us, because India became that time the fourth country where we became the producer of the supercomputer. And we created our own Param series of supercomputer at that time. And in record time of 3 years, we could complete that. So in 91, 1st July 1991, we created first supercomputer. Now we are at a juncture that we are again coming back into the form that we should have our own Exascale supercomputer, which is, that was 10^8. Now it is 10^18. So that is the shift which is happening in the last 30, 35 years. And we are crafting this and hoping that within a 3 to 4 years type of timeline, we will be there back in the Exascale area. So as we to conclude on this note, that India will have a full capability of indigenous design, develop and deploy Exascale supercomputing system. India will move from service economy to knowledge economy, where the gains are immeasurable, and terms of patent royalties and innovations. And finally, through national and international collaboration with the researchers, academia, industry, and startups, India will emerge as a leader rather than the follower. And we sincerely acknowledge the colleagues of CDAC, the Ministry of Electronics and IT, Department of Science and Technology, and partners from academia and industry. And thank you to TIFR, and they are also very, very close collaborators with us. Thanks a lot.
Thank you. Thank you, Dr. Hemant Darbari, for this wonderful tour, if I can say, of the entire journey of the supercomputer developments, deployments, as you said, and indigenously making not just assembly in some way, but making every component, large number of components, large fraction of components, and your applications spanning many fields of science, many fields of natural disaster predictions, digital twins, and speech systems, and so on. And I think the applications must be, there's no end to that. As you said, you can really take these to any level in terms of deployment, as well as also a very important part of exascale machines, which are going to be the super horses for the environment, the weather predictions, and many applications. And some time ago, one of the speakers in the same forum has been saying that, while these exascale machines are quite commonly used in strategic and other applications elsewhere. But India should be what he calls as a CERN. CERN is a world lab for the particle physics experiments and science, and India should be a CERN in this particular field. And I'm sure your scales of 3 to 4 or 5 years of developing this particular and arriving at this another milestone, I'm sure it will be a great high point for us, all of us, and in India. So on that note, I would like to now request, open the talk for questions by our colleagues, and both on the Zoom as well as on the YouTube audience. Please type your questions. I will read the question for you, and the speaker will answer it. The Zoom participants can ask questions directly by unmuting yourself. There is a question from Saurabh Chatterjee. Yeah, please go ahead. Hello.
Yes, please.
Yeah. No, I think Saurabh Chatterjee has a question. So can you please go ahead and answer the question? Okay. There might be some issue. So let me read the question for you. In fact, I think it is there on the chat. How to get computing time on the Param computers? Is it possible to test and optimize astrophysics codes? So that is a question.
Yes, I think we have provided the compute time. There is a small form to be filled, and this is available on our CDAX website and even NSM site also. And you can just fill that form, give the registration, and then we can definitely try to put this request to the team, and they will provision the requirement. You can put your requirements, and that can be taken up.
Okay. So we have another question from Dr. Joshi, Balchandra Joshi.
Yeah. Thank you very much, Dr. Darbari, for sharing your excellent journey from small supercomputers to now exascale and probably zetascale computers. It's quite fascinating to listen to the journey. I had two curiosity questions. One is that you did mention development of an indigenous processor. Is there a plan to develop indigenous GPUs?
Yeah.
And the second question is Airavat meant for commercial application or is purely for academic usage?
Both. Airavat is for both academic as well as commercial, and we definitely are looking forward to provide this systems to the startups and the industry also. And as far as the first part goes, we can work it out how you want to take it up.
Okay. And is there a plan? Is there a plan to develop a GPU, indigenous GPU?
I told that the CPU as well as GPU both have been in the pipeline as a part of the NSM 2.0. So mostly we are trying to take our Vega series of processors, which is RISC-V based processor, and using that RISC-V, we are trying to make our own accelerator as well as the processor.
Okay, Joshiji, then I'll move on. Yeah, I see the Professor Jairam Chenglur.
Yeah, Hemant, thanks a lot for that talk. As Balchandra just said, I mean, it was a very fascinating trip from, small supercomputers to really large supercomputers. And I think NCRA probably has, been seeing this journey secondhand, at least for quite some time. And it was nice to see this, holistic picture of where you all started from and where you all are reaching and going to right now. So I had a couple of sort of similarly like Bhalchandra curiosity questions. One was, see, this exascale computer, of course, is going to, as you said, the number of applications over there are very large, and many of them are of great importance. And they're also in very, very diverse fields. Is there some even preliminary thinking about how, time might be apportioned between these? Because it's not just a matter of ranking ideas. There's also something across fields decision has to be made, because, these fields are very, very different and all of them are important.
Yeah. So I think there are 2-3 things which we are having in mind right now, because these systems are very large. And there are 2 class of applications which generally people have. One is which requires the huge amount of compute nodes. And there are certain things which are required to be generated on a regular frequency. So what exactly we are thinking of is when you require a large number of nodes, like 10,000 nodes or 5,000 nodes or something of that sort, that can be kept for and there's even today we have created an Apex committee wherein these large compute requirements are being put, and then we can provision things wherever the things are going to be made available. Now, in the exascale case, I think we can always have a method by which we can also compartmentalize certain things. Like if a 100 petaflop or 200 petaflop thing can be dedicated towards the exascale systems for earth science. Some domains, some area for the earth, for the life science also. So like that, we can bring them together. And as requirement basis, we can start scheduling the things. So when you require a huge amount of compute and you require a huge memory requirement, that can be scheduled very effectively.
Yeah, thank you. So the other question I had was about this infrastructure for providing high bandwidth connectivity between the users and the machine. See, in some sense, as you were saying, the problem of allocating resources can be, somebody comes up with a proposal, etc. It can be evaluated and so on and so forth. But to create that linking infrastructure, it's a slightly different. I mean, you can't wait for the proposal and then decide, okay, I'm going to provide you the bandwidth because your proposal needs it and so on and so forth, because that'll take too much time. So I was just wondering how you were, whether there was some thinking about where or who all will get this kind of large bandwidth and how those kind of things could be decided.
So you are talking of the data transfer?
The data transfer.
Yeah. So data transfer, I think we are trying to get into this game as soon as we get successful into the POC, because then we will think about how these things can be taken up. Because what is happening is, like 80 kilometers is the upper bound where we can go directly. So like I can mount a storage system, and if you are 80 kilometers away, then I can take you to the system directly. I think your Narayangah is a very
it's a good distance. Yeah,
very good example for that. And I was wondering when we are going to host this as at Chikli Land in Pune.
Yeah.
That can be very effectively being utilized for that. That will be a major game changer, because you will have a much more compute with, like now 1 petaflop is just nothing if we can provide you 50 petaflop or 100 petaflop.
Absolutely. Yeah.
So that is one experiment I am doing, rather we are doing. And then second one is that we can take it up to the, say like Bangalore to Pune connectivity, or even within the see, because what is happening is within the city also there are 2, 3, 4 systems which are available, and now they cannot be utilized either ways. So that is the 80 kilometer thing which we have trying to handle. And as soon as we connect to Hyderabad or to Bangalore or something on a dark fiber with 400 gig type of connectivity, your data can be transferred on just a very, very fast pace. And then you can execute your programs from wherever you are. So like if Ayuka wants to run something in on our systems, so those systems, you don't have to bring the hard disk from the one place to another and deploy it there. So currently it is a major, major bottleneck, and this is what we are trying to address.
Okay, yeah, thank you so much.
Thank you. We have another question from Meghna Mathur.
Hi, this is actually Nilmani Mathur.
Oh, sorry, Nilmani.
Coming,
Yeah, sorry.
coming from my daughter's.
Okay, sorry.
Okay. So Hemant, yeah, again, very nice talk and giving us, sharing your journey to all these things. But I have a question on how will you, like the electricity for these exascale machine will be huge, like maybe
Yes.
40, 50 megawatt, and putting the system in one city, will it be worthwhile? Like, how will you manage it? And then,
Yeah, so I think this is what exactly is the research part which we are talking of. I think the latest architecture which we are trying to work on is rather you will, I don't know, you know or not, but this frontier which is in ORNL US, that is 32 megawatt system, which is one exascale system. So what we are trying to do is this ARM plus GPU, which is a H100. This system can be rigged up in 17 megawatts. So there's a drastic shift if we can, that's why different architectures have been tried out. So this is what is one of the things which we are trying to do. And we definitely have provision for at least 20 to 30 megawatts in Pune. And because that's why I was telling you the systems, exascale systems cannot be many in the country. And the first system or the one system we will definitely create at CDAC Pune.
yeah, so this is what I have the question. The 32 megawatts that they're claiming is, yeah, could be their official number, but effectively they, what I heard, they're taking much more power. And you think the 17 megawatt will be possible in future? That's,
yeah, so that is what exactly we are trying to do. And the power envelope is going to play a major role.
yeah.
And even cooling technologies which are now coming up, these things, there are major research work which is on these areas, because cooling again becomes very important, because as soon as you can cool the systems at to 1.01 PoE type of stuff, that is what exactly will be the requirement. So that's why DCLC has come up in a big way. And now there are other methodologies which also we are trying to do a research on, like CMET is doing very good work onto electromagnetic simulation, and try to see how we can utilize that on the chip. So some of these research is going to lead towards the reduction in the power.
Okay, thank you.
Thank you.
Thank you. So are there any more questions from Zoom audience, please? Okay. Let's see. Okay, so I guess there are no more questions to the speaker. So if not, let us once again thank Dr. Hemant for his really wonderful talk in this as a part of Engineers Day commemorative asset series, and we look forward to his visit to TIFR soon, and hopefully we'll have more in-person interactions with him, and also of course the collaborative efforts that were already on for quite some time with TIFR, and I'm sure they are going to kind of grow much bigger, and along with that the rest of the country, and many of his future plans to go spread things to other cities and improve on the bandwidth for data transmission and mitigating problems like what was just discussed in terms of power, as well as cooling technologies and many other things. And incidentally, I must share with you today, as you are talking here, I was also organizing a workshop on your Vega processors in the city. by your team coming from Trivandrum.
Okay, great.
Yeah, I also did a few other workshops by the same team in other colleges as well. So that's was also happening. I know I had a kind of look at these processors and the way they are sort of in comparison to Arduinos and Raspberries and trying to kind of penetrate into the academic, especially education technologies and academic world. And so there are many directions towards what you spoke, and we are obviously very proud of all your achievements and also future plans. So with that, let me once again thank you, and thank you very much for delivering such a lecture.
Thanks a lot. Thank you.
Thank you. Thank you.